Welcome to my presentation about functors, monoids, and monads. Monads are nomads unlocking the basics. This is the title of this presentation. The title of this presentation has been made as a result of playing out with the word monads. The word nomads is a result of changing the words, and it means really nothing. It's just an interesting title to give to this presentation. And that's it. But what's important is that in this presentation, we are looking at three different aspects of functional programming, and these are functors, monoids, and monads, as we have seen. And the presentation is composed of a compilation of different videos that I have filmed through the months of September through to October, and these are videos that explain these paradigms with practical examples. The talking points of this presentation are functors, monoids, and of course, monads. Let's have a look now at what functors are. All of these paradigms need to follow a different set of rules. For functors, there is one specific rule that they need to follow, and that is they need to have a mapping function, which is called in Haskell fmap, and in Kotlin, for example, it's called map, just as you would see in Java or in Scala, for example. But functors also need to follow a couple of laws, and these are called the functor laws, and there are two of them. One of them is the identity law. And for the identity law, what it says is that if we have a container that is holding a value of type X, and we have a mapping function, and we use a function identity on it, we should get the same container with the value contained inside of it, which is what we have over here. The identity function, all it needs to do is to return the same value that is contained in the container. That's it. The other law that a functor needs to follow is the composition law. And the composition law is a law that is implemented in different ways. If we use Project Arrow, it's usually implemented with the word compose, but we can also use this construction over here. Or we can use map and then map again. What this means is that in all of these three different results, the operation map is applied to a container of value type X, which is what we have over here, and over here, and over here. But the difference between them is that in the first case, we are mapping using a function that is a composition of function f and g. In the second example, we first map using function g, and then we map that result using function f. And at the end, we do another mapping, but in this case, the mapping is the function call of g with parameter that is a result of function f on the value that is contained in that container. So the composition law means that if we use different compositions, the results should be the same. And we have to be careful not to confuse the composition law with the associativity law. That is something different. We will see that later on in other aspects of the other paradigms. And to better visualize functors, we can think of an example. If we have a container, which is this basket over here, with a car on it, and we apply a mapping operation to it with a function, doesn't matter which function is, but with a function that transforms it into a bus, then we should give it as a result a bus inside a basket. And that's it, a one-on-one operation from a container, which is that basket, to another basket that now has a bus. Our functor type here is that basket. Bearing this in mind, we can now have a look at an example in Haskell. And the example is this one. We've got here three different functions, add one, square, and identity function. Then we've got several different printouts to the console. The first thing that we need to notice is that there is a mapping function, and that is called fmap, and this is typical of Haskell. And Haskell has a different kind of code syntax that maybe we are not used to when we come from a Java coding world or Kotlin or Scala or another language. Fmap is used here to the left side of the function that we want to use, and then to the right we have our container with our value. In this case over here is just, here we have nothing, here we have an array. It doesn't really matter. So the order is always, we first have the fmap, then we put our function, and then finally on the right hand side we put our container, or in this case our functor type. But we are testing a list in this case. There are here some tests for just and for nothing, but that doesn't really matter for our test because we are testing list in this case. And in this case we are looking at list to see if list is a functor or not. The next property that it needs to comply to is the property of composition. Now for list, if we use these two functions, they should work in a way that the way we compose them doesn't really matter for our mapping functions. And that's what we see over here in this example. If we combine add one and square together, then the result of this fmap with the resulting function here on this array should be exactly the same as individually creating an fmap on the same array over here, but then doing one at a time. So if we do add one first and then do a square, it should be the same result as this combination over here on this array. And we will see this in the examples following this introduction. The other property that a functor should follow is the identity law. And the identity law says that there is a function, which in this case it's this one, where if we use that function in our fmap, it is the same as not using fmap at all. Well, in this case, it's not a flat map, it's a half map. We need to make that distinction very clearly because fmap in Haskell is not a flat map in Kotlin. So if we use here an fmap, that means the mapping function. That means that what I'm using over here to map this array to another array should be the same result. So as a result of this operation, we should get 1, 2, 3, 4, 5 without any single change. So what this means for list in the case of Haskell is that we have a mapping operation, we can do and perform composition with it, and we can also make a distinct function that provides the identity. And that identity then can be used in this mapping function to give the result that is already containerized in list, and the result should be that same list. It may sound confusing, but you will see in the examples how simple this actually is. But now it's time to have a look at another example, and this time is in Kotlin. Now in Kotlin we may have not seen a lot of examples of this because in the universities many times Haskell is still taught to explain these paradigms. But in this case, let's try and look at it from a Kotlin perspective. So in Kotlin, if we have a list like this one, this tree collection, which is a list of trees, and we map it using this it, essentially we are taking advantage of the identity law. And that identity law then means that the tree collection should be the tree collection if we map it using the identity function. So in this case, the list is cleared for the identity law. But let's see further on what list in Kotlin further complies to. So then we have the mapping function. And in Kotlin is just map. Not an fmap, but just map. And if we have these two functions, so if we have a function where we create a new tree with all blue leaves and only 5 on the basis of the tree passed by parameter, and another function where we create a new tree with only black leaves and only 6 of them on the basis of the tree passed by parameter. And then we try to check for composition. We should be able to prove composition this way. We have a tree collection where we are mapping the composition of G with F. Do you notice something strange over here? If you have, then it's important to explain something now. This compose comes from Project Arrow, and therefore this doesn't necessarily have to be a compose. It could have just been a G of F, but it is compose. And therefore the order here is different than the order in Haskell. And this has purely to do with syntax, but the principle is the same. So this tree collection that is being mapped like this and gives out a result should yield a result that is the same as mapping the tree collection with function f first and then that with function g. And that's what we test over here. So now list in Kotlin has a mapping function, it follows composition, and it follows the identity law, and therefore a list is a functor. This is my short introduction to functors, and what follows now is the video that I have filmed before. I will make the introduction to monoids after this segment. See you in a few minutes. Semantics are a great part of software development. They are part of our communication, and they enable us to communicate our ideas to our peers. When we make software development, it is always better to use small words to define big concepts. This way, we can shorten what we have to say and clearly communicate our concepts and ideas to our peers. There are 3 words representing 3 concepts that are generally not that much used in real-world software development teams. And these are, among many others, monads, monoids, and functors. The goal of these 3 and their adaptation from algebra to software development is to minimize another thing called side effects. All of these 4 concepts are an integral part of functional programming, and if you are not used to them, haven't heard of them, then stick around for the upcoming videos of this playlist that I have called Monads, They Are No Nomads. So let's start with functors. What are they? Functors are essentially types that implement the function map. Is that the only thing that functors do? One thing that it's important to think about when we think about functors is the concept of containers. And what are containers? Containers are structures, data structures maybe, that contain a lot of values. For example, a list is one example of it, an iter is an example of it, an option is an example of it. If you work with Java, Scala, or Kotlin these days, you already have been across these terms like streams, collections, lambdas, etc. All of these terms are related to functional programming. In Kotlin, for example, a list implements the function map. The same can be said for type iter. And the same can be said for optional. And if you have been working with these types, you probably have seen that mapping is very easy to do with them, but what you are actually doing using this map function is using functors, and you are mostly associating functors with each other. The usage of functors in Kotlin help us a lot when we want to transform, for example, a list of elements and make another list with transformed values with it. That is called a functor. But when we think about a list, we think about also other functions that it may have. For example, a filter. A filter, however, does not make a list a functor. And the reason for that is that a filter can reduce the elements contained in that list. And because of that, not all elements get transformed. So that means that by having a filter, it does not automatically make a list a functor. The same goes for count. The same goes for a flat map, for example. Because a flat map may transform the list, but a flat map makes something unique. It flattens the results of all the different containers. A flat map will pick up all the values from different containers, associate them to a new container, and return that container with the new values. But it doesn't strictly apply a transformation that changes the values of each one of the individual elements of the list and returns a new container with the different transformed elements. So we can think of a functor as something that has the property of associativity, so it can be associated with different functors. It implements a mapping function, and this is the case that we see with other containers, like either or optional. But if we think of it that way, how come let doesn't make every type a functor? Because let doesn't have a container context. Let simply returns results. And so a let can return a container with transformed results, but it doesn't have to. That's not the function of a let. And to illustrate that, we can find an example right over here, which I have created in the unit test that we are going to go through to explain what a functor is. In this test, I have created a tree collection. So before we even get into the test, let's have a look at the data created for it. If we go to tree collection, we see that the collection is made out of different trees, in this case 10 trees, and each tree will have 10 leaves, which is this one over here. It's not a very green tree. It's just for testing. And a tree is composed of leaves, in this case, and a leaf has the properties of color and length. These are the two fields that define those properties. This test will first apply a transformation to the tree collection via a map, but before this map is called, this will happen within the context of a let. The let here is just returning a new container with all the different elements transformed by the map. And all the trees will only have one leaf. And this is the test that will check for that. And this is the assertion that will check that every tree will have only one leaf. But important here is that this let over here is only returning the return value of this map. And if we change let to something else, like for example, how about just the same collection? If we return the same thing, it will still compile. And how about if I just create a new collection, 1 to 10, and I say that they are trees. This new collection has nothing to do with the previous collection. There is no transformation being applied to it. And if we just apply map, for example, and we do a map here, and we say tree, we will get a new collection of trees. However, when we apply map over here, we are returning a new collection of trees, but that collection of trees is of the same size as the tree collection that we created for the example. In this case, 10. And this is key to understanding functors. The list of trees is a functor because it implements this map function. No matter what we do around here, we will always return a list of 10 elements. If I put here, for example, a 1, it will return a list of integers with ones in it. But it is still a transformation. We just transformed one tree to number 1. And now we have a list of 10 elements, which are different 10 ones. But this is why let does not make a list a functor, or any other type of functor. If we check on the next test, we will see the actual reason why list is considered a functor. And the reason is because of this map. And now it's more visible because now we are transforming every single tree into another tree with the same leaves. It is a transformation, a kind of identity transformation, and the new list will have size 10. This next test does something even more special. It transforms all of the trees into new trees with only one leaf, and each individual leaf of each individual tree will be colored pink with a length of 100. And that's what we test over here. We test that it has size 10. And here, instead of for each, we can do a should. We can do a for all, which will test that every single tree has only one leaf, that the first leaf is not null, that the color is pink, and that the length is 100. The next test will go a bit further, and now we will test option. And interesting here is that I'm using option from arrow. We can go here upwards, and we can see that I'm using option from project arrow. And this option has something interesting, which is something that is also used in Scala, but now adapted to Kotlin. And what we do here is something similar, but with a different taste. So if we go over here and check what has been tested here, I made it a bit more complicated because it is very important that we get this concept right. So I have created this object reference named make tree empty. That is an option tree, but not an option tree. It is an option of a function that accepts as an argument a tree and returns another tree. And I create an instance of this option by using sum and using as an argument a function that simply will make a copy of the current tree to another tree with no leaves on it. Once we have that make tree empty option, we can use it kind of in a function way, and we can map it to be able to use it by doing this, and then using it to call the function and perform a transformation to a tree of 10 leaves, and then check the results with fold. This operation will not throw any errors, but the assertions are ready to capture errors should they occur. We can of course use option to make some sort of error handling, and in this case that is precisely what we are doing. Imagine for example that the result of make tree empty is actually a null value. So let's change the code a bit to test that. If I remove here the tree copy leaves empty list and put here a null, I cannot compile this because tree here, the return, needs to be nullable. On top of that, here down below, the result tree comes up as nullable, and that means that potentially is null, meaning that dot leaves would not work. But this with a question mark is not the best thing to do. What we should do is result tree and assert that it should not be null. And here we come to the point of this unit test. What do you think will happen when I run this? Will the code fail over here in this assertion? Will there be anywhere else in the code that the runtime will fail? Will it fail here? Will it fail here? Where will the code fall? Will the code fall in if sum, or will the code fall in if empty? Let's analyze that. We are returning null. And by returning null, it means that we are not returning an empty result. In fact, if empty here would be impossible because we are always returning either a tree or a null value. And so the only possibility is that the code falls into here in if sum. If our tree has no leaves, then the return result will be a tree with no leaves. And that means that these assertions, these two over here, will return no error. But if the result is null, we will still fall in if sum, and by doing that, that means that the result of result tree will be null. And that means that the code will probably fail right over here. But let's see what happens when we run the test now. And look at what happened. Right over here, where result tree should have not been null, it is null. And this is only possible because of option, and because in this case tree will never be an empty object because it's not a container. The container here is the option where we have placed the function that we have used in this case. That means that we've used the function, we've mapped it to receive the return value from a tree of 20 leaves. The result is an option of tree that we then fold, and doesn't matter the process of folding in this case, we will always fold in if sum, and this if empty will never be called, and that means that we can either get here a null or an empty tree. If I now revert the whole code and run the tests again, we can be sure that the test will work, because here at the result tree we will get a tree with no leaves. Let's run the test. And that's exactly what we get. A successful test that confirms that we get a tree with no leaves. But these aren't the only functors that we can use. And to illustrate better what are functors, I have here other examples, and the first one is with either. This either comes from Project Arrow. I have discussed this before in this channel, and if you haven't seen the video that I have created about higher level concurrency in Project Arrow, I recommend that you do that now. But if you have, let's have a look at how this either is implemented. When we call this either, the goal is to call our function and have a return value of either that could be on the left an error and on the right result. And we create a tree with 20 leaves, and then we copy that to another tree that doesn't have any leaves. When this either is finished, the result is stored in create new empty tree. If we fold the create new empty tree, then we are going to have two different functions that we need to implement, a bit analogous to option, only that in this case we are actually checking for errors and for a successful result. If we have a fail, then we need to implement if left. If we have success, then we implement an if right. We need to give both arguments to fold, and then upon getting a successful result, we then check if the tree is null or not. It will not be null, but we can check it anyways, and then we check that it doesn't have any leaves. This will be this result, which we can then use to map that tree to its leaves. And this is a mapping from one tree to the list of leaves. So it's still a transformation of one element to another element, which in this case, it is a tree to the container of all the leaves, in this case the list of leaves. The return result will also be an either, but in this case that either has on the right the leaves of that tree, which in this case is an empty list. We can then fold it to check what happened, and then we can try if left, that means if any kind of error has occurred. We can then fail the runtime of the unit tests, but this won't happen. What will happen is that it will be successful. There will be a call to the if right function that we implement over here, and here we will only check that the list of leaves that we have taken out of our tree is actually empty. So we have seen a list, which is a functor, we have seen an option, which is a functor, and we have seen now an either, which is also a functor. But then at some point we can carry this definition with us and find functions that sound and seem to behave like functors, but they are not functors. One of these examples is the end-then function. So for example, in this unit test, I am creating two functions. The first function is add 5 leaves, and the second function is divide leaves by 2. The first function will add 5 leaves to a tree, and the second function will divide the leaves by 2. Important to notice and to repeat, there is no transformation to the original tree. It will add the leaves, but under the hood it will actually create a new tree with 5 leaves on it. The same goes for the divide leaves by 2, a new tree with half of the leaves of the original one. And then what we do, we use and then to join the two functions. So in this case we are creating an association between the first function and the second function. And the idea is that when we call the add 5 and then divide by 2, that we do exactly that. We add 5 to a tree, or better said, we create a new tree with 5 extra leaves, and then we divide the total of the leaves of that tree and create a new tree with that amount of leaves. The result will then be for an empty tree. It will add 5 to an empty tree, and then it will divide by 2. It will add 5 to an empty tree, and then it will divide that by 2, which will be 2.5, which rounded up is 3, which is what we expect here. We can then make another function association where we do the exact opposite, but instead of calling and then, we call compose, which is an interesting one because it associates the two functions, but in a reverse order. So in this case, we do a divide by 2, then add 5, because we are saying that we want to compose a function between add 5 leaves and divide leaves by 2. In any case, the result here will be 5, because we are dividing 0 by 2, so that means 0 leaves still, and then we add 5, which amounts for the total of leaves for the new tree. So here we have two associations. We've got add 5 leaves and then divide leaves by 2, and add leaves, compose divide leaves by 2. So the question is, how is this associated with functors? It's not. Because although we have and then and compose, and they do associate two functions, neither one or the other function are containers. And the result of using these functions is also not a container. So we don't have anything special here that keeps the container, because there's no container in the first place. Why can this potentially lead to confusion? It's purely because the function itself may seem like a container, and because we can associate these functions with and then and compose, it may give the feeling that we are in the presence of a functor. However, that is not the case. No container is involved. There is a transformation that seems to be running within a context of a container, but in fact it's just values being tossed around through the two functions to get a final result, which is not a result inside a container. We just had a look at how functors work in Kotlin. Let's now have a look at how they work in Haskell. Why Haskell? Because Haskell was the first pure functional programming language, and it was created in 1987, and it was released to the public in 1990. So it has been around for a long time. But one of the things that Haskell does is that it clears it up as to why these principles were invented in the first place. And for that, I have created a few examples that we are now going to have a look at that are similar to the examples that we have seen in Kotlin, but there are going to be curiosities in there that are also important for our understanding of functors. And remember, these things that we are having a look at that are functors may also be monads and may also be monoids. But for now, we stick to the definition of functors and we explain them under that angle. So the project is located on GitHub, and it is a new project called Haskell Test Drives. So this is a project that I am creating to include examples made in Haskell. And let's first have a look at how it is built. These examples are organized through topics. There is only one topic at the moment, and it's called functors, and inside we have different files that can be compiled into native executables. And the compiler is GHC, and GHC can be installed pretty much the way that I have defined it in the make file. So let's look at it. It's over here, and then inside we have an install script that has the update for apt, and then we only need to install GHC and cabal install. Once these are installed, we get GHC available in our command line if you are using Linux. Make sure to look for the right documentation to install GHC in your computer should you have a different operating system. I am using Ubuntu in this case. And in any case, if you have questions about this, make sure to leave a comment in this video or in the community section of this channel. So let's have a look at the first example, and the first example is called make list. As we have seen before with Kotlin, list is a functor. Why is it a functor? Do you remember? It has a map. It allows to create a transformation maintaining the context, and it applies to a value. That's it. And the result of these mappings is also a functor that can further be mapped. In the first example, what we have here is two different functions. The first function is add1 and the other one is square. We can use these functions in our mappings, and what we want to do here is prove that list is a functor. But here's the important thing. When we use fmap in Haskell, we need to make sure that we are using it in combination with a functor. And this is key to understanding how they work. And so in our main function, we see that the first line of code is a mapping to something called a just, and just only has 5. This is one kind of functor that allows us to map this just 5 to another result, and the result will be a combination with this function. And in the second line, we see that we have nothing, and we try to add 1 to nothing. So essentially we are trying to map nothing, which is also a functor, and mapping it using the function add1. In the third line, we are adding 1 to all of the values of this list. On the fourth line, we are squaring all the values of this list. And finally, on the last line, we are only printing the list. Let's run this program and see the results. For that, we first need to compile the HS file, which is HS in this case stands for Haskell. And let's do that by running ghc and then the file name, which is in this case 1_maplist.hs. With this command, we have compiled the file, only in this case we haven't, because I already have the file available. But I want to show you exactly how the compilation method works. So in this case, I'm just going to go here to the root and just call a make clean all. The clean all script removes all the files in the Functors directory that have been created using GHC. GHC creates intermediate files. It creates an O file and it creates finally the executive native file. And this is everything that we are deleting in this line over here. And then here we delete the O files, and then here we delete the high files. Let's run clean all. Now all of the files that we have generated with GHC have been removed, and now we can continue with our example by going to Functors. And in Functors now we can run ghc 1_maplist. And now we see that it has compiled main, it has created an O file, and it has created the map list executable native file. And we can also see in the middle that it has created an intermediate compiled file, which is this .hi file. So let's now just run it. If we run the executable file 1 that we have just created, we see that we get as a result a just 6, which is adding 1 to just 5. We get nothing, because if we add whatever it is to nothing, we get nothing back. And on the other 3 outputs, we get the original list with the 1 added. We get another list of the square result of every individual original element. And then finally, we get the original values in the end. So what is magic about this? In all of these examples, we have been using functors. And they go very well with this fmap. For example, if I would just say here add 5, 5 is just a value. 5 is not a functor. So applying map on it wouldn't work. So this fmap over here should fail. If we try to compile this now, we see that it says no instance for num arising from the literal 5 in the second argument fmap, namely 5 in the first argument of print, namely fmap add 1 in the statement of a do block print fmap add 1 5. The compiler doesn't know what to do with this, and the reason for that is that 1 is just a value, it's not a container, so the context cannot be maintained. It wouldn't make sense to have a context with value 5, because in the end what we want to do is present the result of this mapping after calling it. But this probably is the easiest way to understand functors in Haskell. But there are other situations that are a bit different and may be more confusing. Like for example in the case of functions. Remember that we just left the examples in Kotlin with a curious case of and then and combine, that we have established that they are not functors and that they don't belong to these kind of paradigms. They don't belong to these kind of paradigms because they are not being used to combine functors. They are being used as extension functions to join 2 other functions, and that has nothing to do with functors. However, Haskell has a very ingenious way of using functions as functors. So let's have a look at how this other example is implemented. In the first example, we are establishing that we have a function that will multiply any value given to it by 2. The second function, plus 3, will add 3 to any single input. And then we create our first combine function, which is also a functor. The plus 3 by 2 means that we first add 3 to a result, and then we multiply it by 2. And that's what happens with this fmap. But notice that I'm using fmap between two functions. This is something that we wouldn't be able to do with map in Kotlin. And that is because those functions that we are trying to join in Kotlin, they are functions. They are not functors. And so we cannot map them. We can use extension functions of Project Arrow to combine them together, but that is not the way functors work. And we can go even further, because here we've got a plus extra. So this is just an extra element that I can add to the logic behind plus 3 by 2. So in this case, we add 2, and then we pass on that value to plus 3 by 2. But what actually happens here is that we are joining all of these functions using map because they are functors. The context maintains, and what happens is that this plus extra and this plus 3 by 2, these two new functors are combined in the compiled code. In Kotlin, the functions are seemingly combined, but they are not actually combined in the bytecode. What we get in Kotlin is something that works kind of like a functor. It kind of operates like a functor. It walks like a functor, perhaps, but it's not really a functor. This, however, is a functor. And so let's test it and see what we get as a result. For that, we already know, we just use GHC and then example 2, and then we compile the Haskell source file into our native command. It will still generate the O file, it will still generate the intermediate compile file, but it will give us the native code that we can now call from the command line, and that is toMap function. By calling it, we see that the first result is 26. Why 26? Because I'm applying plus 3 by 2 to 10. What happens over here is that we added 3 to 10, and then we multiply it by 2. We get 26. And then in the second one, we are mapping a list of 1, 2, 3, using functor plus 3 by 2. This is a strange concept, but it works. Because since both of them are functors, what happens now is that the plus 3 by 2 will apply to 1, 2, 3. The function is used as a function and not exactly as a functor. And as a result, we get a result of 1 plus 3, which is 4, multiplied by 2, which is 8. And then the same for 2. 2 plus 3, 5. 5 times 2, 10. And then 3 plus 3, 6 times 2, 12. And then finally, the last result, which is a 10, where we add then a 2, that's 12. Then we add 3, which is 15, and then we multiply by 2, where we get 30. But the great thing we can see already here, these were all functors, so we were able to combine them all in a single line to perform certain operations that would otherwise be more complicated to implement. In the past two examples, we have seen that lists are functors and that in Haskell, functions are also functors. But we can have a look at more examples, and one of them is with either. If you remember from the beginning, we were using Project Arrow to access these types. These are either, right, and left. And from that, we know that right is where we put the successful result, and left is where we put an unsuccessful result, which can be an error, an exception, or anything we want it to be. In our example, if we go to map either.hs, we can see that we have a right value that has been created by using a right that is of type either, of course, and it accepts a string as an error type and an integer on the right side of it. So this means that our successful value is an integer and our unsuccessful value will be a string. But we are not only declaring it, but also assigning it a value, which is already right 5. And what we do after that is that we print the mapping of a function that adds 1 to the right value. So this means that the right value is right 5. The function adds 1. And so after mapping, we should be getting a 6. And it's not just a 6, it is a write 6. And this makes write, in this case, a functor, and it also makes either a functor. And the second write value is made by using fmap of a function that adds 5 and the write value, which is 5. So in this case, the print second write value should result in a 10. Finally, the left value is an error, and it is a left string that has error in the description, and that error is of course a subtype of either that on the left has a string for an error and on the right has the value integer. And if we try to print this by making a map between a function that adds 1 to the left value, what do you think it will happen? Are we going to get the left value with error anyways? Is this going to fail? Or is this going to add 1 appended to the end of the error string? What do you think it will happen? Let's have a look. And for that, we are already in Functors. So in this case, we only need to compile it. So we just run ghc 3_map either, and this will generate the native file that we can immediately run. So if we do .3 map either, we can see that on the first result we get write 6. On the second result we get write 10, as we mentioned before. So we can see in our last example that we get a left error. What happens in this case is that we have added 1 to the left value, right? Not exactly. What actually happens is that left and right, both of them are either. And that means that because they are either, they are also functors, because either is also a functor. And what happens in this case with either is that when we add a value to an either, like in this case, like when we do here +1, it will add that value to the right value if there has been no error. If this is already a left, that means that whatever mapping we want to do with another functor, the combination will still result in the left original value. And that means that the last original value in this case is error, and that is the result we get, a left with an error string. And as we can see here, an either is a functor simply because we are able to apply this fmap, and that in the end we get another container that is another functor that we can then apply with another fmap with another functor. But there are other examples that are also very curious in Haskell. Another one is with IO. And the IO may seem a bit strange if you are coming from another language again. It is different. And the way it works is that it establishes a set of rules, a set of operations that it wants to make. And every time we want to get the result out of those set of rules, that is this reversed arrow. This reversed arrow can also be used to scan results out of the console, for example, as we try to input data to our program. And what this program is doing is simply simulate that. And that means that when we first start the program, we declare our first functor that is now an IO of type int. To declare an IO of type int in Haskell, you can do this, a return 5. This will return our functor that then we can map using this fmap again with a function that will multiply the result by 2. That means that when we get this result over here, we will get 5 times 2, which is going to be a result of 10. And this is interesting because as we do this with this reversed arrow, we extract our result out of the container, and that means that this result is just an integer. In our second call, we are creating a double result, which is another functor that is a result of combining the two functors, which is the function that multiplies it by 2 again, and the IO mapped result. This results in a functor, and to extract the result out of that functor, we use again this reversed arrow, and that result will be stored on result 2, and then we print result 2, and that means that we will see a 20 in the console. But let's try it and see if this matches with what I just said. We first compile our program in the same way as we did before, and now we can just run our newly compiled native executable file and see that we get 10 and a 20 in the console. This 10 and 20 are integers, these are not functors. The functors we got are these two. We could ask ourselves, why didn't I print also the functors as I did before, the IO mapped result and the double result. Well, these are IO functors, and IO functors in Haskell are not easily printable to the console. If we try and do that, we will get an error, and I'll explain that in a minute. So if I can try and print the IO mapped result, and then I can try and print the double result. This will result in a failure, which is this one. And if I show you what it is, we can see a text here that says no instance for show IO int arising from a use of print. What this means is that these functors, the two of them that we have created, IO mapped result and double result, both of them do not implement this. And in Haskell, you need to have this in order to be able to print out results to the console. But we know that we have created double result using an fmap between two functors, the function that multiplies by 2 and the IO mapped result. And this could have only been possible if IO mapped result itself an IO also is, which means it is also a functor that can then be mapped using a function that is also a functor that multiplies the result by 2. Which also means that we can only see the results working by printing the result, which is using this reversed arrow. We have seen 4 examples about how to work with functors. We have seen a list example, a function example, an either example, and an IO example. All of these 4 examples were specifically made to understand about how functors work. In this next example, we are having a look at a custom functor that we can also make in Haskell. It is a different concept, and it is important because here we are going to see a different way that functors can work for us. In the first line of our code, we can see a save vault. This is a data class that is being defined with this type save vault, and it is deriving from show. This is to be able to print our object into the console. As we have seen before, without this show, we cannot print functors to the console. In this line over here, we are associating a functor to the save vault. And what this means is that we can then use save vault as a functor. We define a function that will double the value of whatever argument we pass through. And here we begin with the most interesting part of our exercise. And that is how to use save vault as a functor. As we have seen here before, when we define a functor with save vault, we also need to implement the fmap function. So how does this work? Here we've got a save vault that will use the function f, which is in this case is double, and we'll apply this function to this value over here. Having this in mind, it will then convert that into a new save vault. This is a simple way to implement a functor. And because now we say that save vault has an fmap implementation and uses that fmap to create a context to perform operations, we can now call it a functor because it will also generate a functor at the output of the call to fmap. In this case, when we call an fmap from a save vault with value 10 to a double, the result will be a save vault of 20. And in our main function, we can see that we are printing custom result to the console. This is where we are going to see in the console a save vault with a value of 20 in it. In the second line of our main execution, we can see that we are mapping custom result to double. The value inside our save vault that is now 20 gets doubled and turns into 40, and that means that outside of this function we're going to get a save vault with a result of 40 in it. So it will be a save vault 40. And then finally we can just see an example of how double can be applied to map a list of 1, 2, 3, 4, 5 using the double function. And this way we can also see that the double function functor can be used either with the save vault or with a list, and that is because both of them are functors themselves. And so mapping in these cases always work. So in this case we will get a list of 2, 4, 6, 8, and 10. Let's now compile the code and see it working. If we run ghc 5 map custom.hs, we're going to get our native executable file, and then if we run it, we're going to get a save vault 20, a save vault 40, and a list of 2, 4, 6, 8, 10. And one important thing here that we have also seen in other examples is that it becomes more clear that functors can interact with each other, and we can perform fmap operations to keep the context of execution of our values and make them work together as one single functor. Because in the end, what we always get is a functor. But let's make this even more clear with the second example, which is the map composition. Map composition is an interesting example because we are working with composition. That means we are working with functors that are going to work kind of like a joining of two different functors, but instead we are first creating two different functions that will work in separate contexts, but instead we are just saying that one function will be executed after the other with the output argument of the first one. And this is important because then we can see something that is more similar to what we saw in the Kotlin code with and then and combine. So let's begin from the top. In the first few lines of code, we can see that we have a function increment, which essentially just adds 1 to the input parameter. Then we have another implementation of square, which essentially squares the input parameter. And then we start with creating a maybe of type int, and that maybe is already a functor. And what's interesting here is that we are going to create a maybe with just 5, and then we are going to map it using the square and the increment combined together as functions, not as functors, but just as functions in this case. So what will happen here is that we receive 5, and inside the functor 5 will be then incremented by 1, and then it will be squared. So that means that we will get 6 and then 36. And only at the end we will get a new functor of type just. Over here we have a different example, and that is simply a list of integers. So we define our composition list result1 as a list of integers, and then we apply the same mapping. So we use fmap to map 1, 2, 3, 4, 5 to another list that will have different elements, and obviously in this case it will be for example for the first element it will be 1 plus 1, 2, and if we square that we will get 4, and so on. But what's interesting here is that for every single element, what will happen is that the combination of the two functions will receive every single value of the list inside the functor, which is the combination of these two. And only at the end, after performing the calculation, we will get the new functor, which is going to be the list of the transformed results. In our main function, we create something interesting, which we first print out the result of composition maybe result1, then we print out the result of composition list result1, and finally we do something different, which is applying the same fmap with the same function combination square and increment, and then we apply that to composition list result1. So this means that composition list result1, which is a functor that is a list, gets mapped to the combination of the two functions square and increment, which combined will allow the creation of the new functor, which will be the result of this fmap, which will be the list of the resulting numbers. We still have 4 examples to go. So let's look at our next example, and that example is about containers. In this case, the specific container we look at is map, and in this example I have created first a map of strings and then a map of numbers. The map of strings contains a map that is composed of strings where the keys are integers, 1 or 2. And this map is created out of a list of pairs, and the first pair has value A, which is a string, and is associated with key 1. The second pair has a value of B, and B is associated with key number 2. And then we create a map from this list, and then we associate that with the map of strings. The same thing goes for map of numbers, where we create then a map from a list that is composed of 2 different pairs. The first pair has value number 1, 2, 3, associated with integer 1, and the second value has a value of 4, 5, 6 associated with key number 2, and therefore we create a map of numbers. The third line of our execution prints out the map of strings, and the fourth line prints out the map of numbers. The following line prints then the interesting part about this example, which is calling a map and transforming the first map of strings. Now, map of strings in this case is a functor, And that's the reason why this fmap can be called with the function that's associated with it, and this is this one. This is simply a concatenation of strings, and this means that z will be appended to value a and value b. In other words, the z string will be associated to all of the different strings, which are the different values of that map. And in the final line, we add 1 to every single value of the map of numbers. But let's run this and see this working in action. The first thing we do, we compile our example, which is number 7 underscore map containers.hs, and then we get our native compiled file that we can immediately run. And when we do that, we can see the result, which is, for the first result, we have a printout of the complete list, which is a from list of the two different elements, the two different pairs, 1a, 2b. In the second output, we see again the map of numbers 1, 1, 2, 3, 2, 4, 5, 6. And then in the third and fourth lines of our output, we can see the transformed maps that we have created. The first transformed map has now the z appended to its values, and the second transformed map has a 1 added to its values. And this makes us see how a map is a functor. But we can also try another thing. Let's see if we can create a different map. In this case, we can create a map of numbers 2, which is going to be the f map of 1, for example, and then map of numbers. We can now do something different, which is we can map then the result and then say that we want to print out the map of number 2. If we now compile this file again, we should be able to see, by running it, the final output that we're going to get will have the first value as 126 and the second value as 459. Let's see if that's true. The first value is 126 and the second value is 459 because we've added 1 on the first instance, and on the second transformation we added 2. But what's important here is that we were able to make successful calls to fmap, which means that every single result of fmap is another functor, which is a property of functors. Bearing this in mind, we should now be able to look at more complicated examples, like for example the map tree example, where we create a tree. This case represents an implementation of a binary tree, and what it does over here at the top is we declare a tree, and the tree can be a leaf or can be a node, and the node itself can be a composition of two different trees, and thus creating a binary tree. In order for this to work as a functor, we then need to implement at least one fmap, and the first fmap simply represents the mapping to a leaf, and the second fmap represents the mapping to a node. Finally, we can see a running example of this implementation, where we first create a tree that is composed of a node that contains 2 leaves, and then at the end we print out a tree that is a transformation of one added to all the different elements of it by means of an fmap. And that means that the result will also be a tree, and this tree can then be fmapped again. But let's first compile the code and see it running. So we first make an GHC. We first compile the map tree example, and then we run it like this, and then we can see that the tree that we have generated is a node that contains 2 leaves that now have values 2 and 3. We started out with 1 and 2, and then we added 1 to every single element of that tree. And now we can see if this tree is actually a functor. We already know that it implements an fmap, but does it work as a functor? For that, we can just print again, or for that we can just create a tree. Let's call it tree2, which is going to be the result of using an fmap to add a 3 to the original elements of tree. Then we can do a printout of the fmap of tree2, and then we can print out the result of the transformation of this tree, where we then add a 1 to every single element of that tree by means of the fmap. So now if we compile this example again, GHCH map tree, and we now run it, we can then see that the last result is 5 and 6. The reason why this happens is that we first added a tree to 1, that's 4, and then we add 1, that's 5 for the first leaf, and the same thing for the second leaf, where we essentially add a tree that results in a 5, and then finally we add a 1 that results in a 6. These are different trees, and they are the results of doing different mappings. This is what a functor does here in this example as well. Now let's have a look at something a little bit more simple, and that is another example of maybe. But we have seen this example a while ago in another exercise. For this exercise, we're going to go a bit deep and understand more how maybe works. That example is located on this file, 9map maybe, and this file is the implementation of the example of maybe. So let's have a look into it from the top to the bottom as usual. So here at the top we have a declaration of a function called increment, which receives as an input parameter a type int and returns another type int. Increment is implemented in the following way over here, which means that it will add a 1 to the input parameter, meaning that it will just return an addition of 1 to whatever parameter we put in through it. Over here we have the declaration of a maybe. This is maybe of type int, and then immediately we perform an operation in it. And this operation is via an fmap from just 5. We have seen before that just is also a functor, and this is a just of number 5. As we increment it, we increase the value that is inside the container from a 5 to a 6. So this maybe result 1 will be a just 6. Then we find maybe result 2 that is also a maybe of type int. And immediately we perform another operation. And in this operation we will try to increment from nothing, which is also a functor. But which value do you think maybe result 2 will hold after performing this operation? That is what we'll see when we run this example, and we can already investigate what happens in the main function. In the main function, we see that we first print out the result of maybe result 1, then we print out the result of maybe result 2, and then we print out through an increment through a list. So we should expect over here to find a list of 2, 3, 4, 5, and 6. Let's run this example now. And for it, we can just run GHC, and again, as usual, just compile our Haskell file. As we do that, we are now able to run the native executable, and what we see is that indeed we get a just 6, and as you probably had expected, we get a nothing out of the maybe result 2, simply because when you have a nothing and you try to map it to something else, and it's just a simple operation like this, we just get a nothing back. And in the end, we get a full list with an addition of 1, and this is just to see that increment doesn't have anything special to it. It's just a function, which is also a functor, but in this case, it's used as a function just to change the values inside the container, which in this case is a list. But to check if these are functors still, we should check if when applying fmap, we are still going to get results. Let's see that, and the first thing that we are going to do is to create a maybe result 3, and we will assign it the mapping operation of adding 2 to, for example, maybe result 1, which we have just seen that it has turned into a just 6. So if we add 2, we should now see a just 8. Let's see if that's what happens, and for that I will print out the maybe result 3. And now just compile the code, and that's a map maybe.hs, and now we can just run the code and see what happens. And as you can see, the first line remains just 6, then nothing, then 2, 3, 4, 5, 6, and then finally just 8 as we expected. So this was the last example of our series of examples about functors. But let's have a look at another example, which is the bonus example for this topic, and that is the bonus 1 map tree. The bonus 1 map tree is a bit more elaborated example, which intends to focus on everything that we have learned so far about functors in Haskell, and it tries to give us a better perspective on how everything works. So let's start from top and go all the way to the bottom as usual, just like we did for the other examples. At the top we find the declaration of type tree, and tree can be a leaf or a node, and that node can have 2 trees associated with it, making by this whole declaration a binary tree. And in order for the binary tree to work as a functor, we need to create an instance of this functor, and associated with tree, where then we have two different implementations. One of them is the implementation of an afmap for a leaf, and the other one is the implementation of the afmap for a composed node, which will have on the left one node or leaf, and on the right one node or a leaf, or a node or a tree. Following that, we see a declaration of something different, and this is the build tree. We can see that the build tree is also an IO, and it is of type tree, which is of type int. In this case, this is also a functor, so build tree is a function that it's also a functor that is of type IO, and it returns a tree. What we want from this function is a tree that will only have one sublevel, and every single node will have leaves associated to them. In the first case, we ask for the value of the left leaf. Think of it as a tree that on the left it has a node with a leaf, and on the right it has a node with two leaves. Every single leaf will have a value associated with it, and in the first line we ask for the value of that leaf on the left. The way we get the values from the console in this case is by using readline. And readline itself is already an IO, and that way we can extract the data from that readline to the left node left leaf value. Readline is something interesting because if you remember from the examples before, an IO allows us to get values from a certain source and then extract using this arrow over here. And in this case we are simply scanning for a value from the console. The second value that we need is the right node left leaf value, which is the value of the leaf located on the left hand side of the right node. And finally, we need the value of the leaf that is located on the right node, and that's why we call it right node right leaf value. Finally, we build a tree with this instruction over here, and this tree then is composed by a node and then by a leaf, which then we put in as this left node left value. Then we create another node which will have now two leaves, this one which we fill in with this variable over here, and then finally on the right we fill in with this right node right leaf value, which we have put right over here from this readline input. Finally, we return the tree. On the next declaration we define our main function, and our main function, which is also an IO functor, is our entry point of our application. And the first thing we do is call the right build tree and associate the return value to tree. So this means that we'll go through all the different inputs, get our new customized tree, and then continue with the execution of the program. We print the tree to the output, and then finally we add a number to all the leaves associated to the tree. And to do that, we get the number again via a readline. When we get this number in the num variable, we then are able to do an fmap by adding this num to all the elements of the leaves of the tree. And this is accomplished by using this half-map. This fmap will call precisely what we have defined over here. And this means that it will trigger a cascade of additions throughout all the leaves inside our binary tree. And that means that at the end we will get an updated tree with the number that we've decided to add to all the leaves to it. And to see this working, let's now compile our program and run it from the command line. So now we can just compile our bonus example. And to do that, we just need to run ghc bonus map tree.hs. And now we should have our natively compiled auto-executable file, which we can then run like this. And now we only need to enter the values for our tree. So for the left node leaf, we just say, for example, a 4. For the right node left leaf, we can put a 6. And then for the right node right leaf, let's say a 10. And now let's add a number to all the elements of the tree. Let's say 2. What we get is a tree that has a left node with a leaf with number 6. This number 6 was achieved because if you remember, the first number that we have set for our left leaf was number 4, and then we've decided to add a 2 to all the elements of the tree. So that means now we have a 6 on the left side. The same thing for the node on the right and its leaf on the left side. We get an 8, and the reason we get an 8 is because the second value we added was a 6, and now if we add 2, then we get an 8. Finally, the same thing, leaf 12, we have set a 10, and then we've decided to add 2 to all the leaves, and that means here we get a 12. But let's make the last test, and that is, again, to create a new tree. So next tree, and let's just say that This is going to be resulting from an fmap of the last tree, where we are going to apply a 5 to all the elements of that tree. So this is going to be the updated tree that we will map to the new one. And then we will print the resulting tree. Next tree. If we now compile this program, we will see exactly what I've just described. So if we say GHC bonus map tree HS, it should now compile. We've got the new command, and then we just run it like this. And now let's just say, for the sake of comparing the two examples, let's use exactly the same values. It was a 4, here we had a 6, and here we had 10. And now let's say we want to add 2 to that tree. We've got the same result as before, 6, 8, and 12. And look what happened now in the next nodes. The next tree has been mapped with this function that adds a 5 to whatever element they have inside, in this case an integer. And in that case, 6 plus 5 is 11, 8 plus 5 is 13, and 12 plus 5 is 17. So this example, which is a bit more elaborated, showed us a few things in action. The IO functor, it showed us also the actual way to declare a functor. It showed us how IO works in the return values of functions, and it showed us how to get values from the command line using readline and how that works with IO. This finishes our examples about functors in Haskell and Kotlin. The next concept for our study is monoids. What are they? How are they used? How do they differ from functors? And how does that lead to monads? So that was my introduction to functors in this video. I hope you've watched it till the end. I know it's long, but there are a lot of details there and also a lot of examples, which I hope made it easier to understand what functors are. Now it's time to have a look at monoids. And monoids are different than functors in the sense that they do not preserve context. They are specifically designed to act on binary operations where both operands are of the same type as a result. Type here is very important, which is something different than what functors did. In functors, we have seen that you can get a new container which has to be of the same type, but the values can be different. It can even be a different type, whatever is contained in those containers. So they can hold on to different types and different values. But with monoids, that's also different. But let's see. The first property is called closure. This property, I just mentioned what it is. The result has to be the same type as both operands. Then monoids need to have the property of associativity, which is different than the property of composition. Composition is more related to the hierarchy of calls and how those result in the same thing if we make them separately. Here is more about the order to which we use the binary operation, which is also called the combine operation in this case. And another property that the monoids have is the identity property. For functors, we have seen that that is a function when we talk about identity. The identity property of monoids in this case is actually a value. There has to be a value that belongs to the same domain as the value that we are using in our binary operation. So for example, if that value is A, then the identity must be something that used in the combine operation will result in A again, no matter what the order we use for that identity value. And the identity could be any value that complies to this property. For example, for lists, if we use an empty list, a literal empty list, then that would be our identity for the list type. If, for example, we want to use 0 for the integer in binary operations like plus, then 0 is our identity. 1 would be our identity for multiplication. Identity means exactly this, that the order doesn't matter and the result will be the value that we are combining it with. But let's picture this in a more visual way. For example, if we have a car and we add it to a bus, what should be the result? Which result should we be getting as an output? Think about it. What would it be? I think in this case it could be anything we want. And if I say this, well then we have a car and a bus. But the car and the bus need to be of the same type as their types individually. So that means that this representation leaves a lot to the imagination. What would be the type of combining car and a bus? Maybe a vehicle, maybe a new vehicle that is a combination of the two of them. The point is that a binary operation, it just needs to have the same types everywhere. So if we say, for example, that these two individuals, the car and the bus, are part of a list of one element, then this checks out. That means that the list of one car, of one element, and the list of one bus, one element, will result in a list of one car and a bus. But we can also think about this example in another way. If I have one vehicle, which is one car, and another vehicle, which is one bus, then I have 1 plus 1, and then I have, as a result, one car, one bus, and that's 2. 1 plus 1, 2. So 2 integers, and the result, another integer. So all of them then are integers. The whole point of this is to make us think, how would we use this image to give us a binary operation? Because that's the whole point of monoids, binary operations. And so we can now look at one example in Haskell for this. And this one is a very easy example because it's all about numbers. So the first example is the identity example. Haskell, for types that are monoids, implements something called a mempty. And the mempty is our identity value. Mempty in this case is a value that represents an empty list. So that means that if we use it in combination with the combine operator, we will have the same list that has been combined with this mempty. So that leads us to the binary operation, which is called a mappend. So we can say it in this way. If we use mappend with mempty and a list, the result will be that list, no matter if mempty is used on the left-hand side or on the right-hand side. And for list, there is another property here that we can see that happens with mempty. Since mempty implements a concatenation of lists, the result of list 1 combined with list 2 ends up being the same thing that we say when we concatenate two lists. It will be a combined list, which is what gets printed out to the console over here. So we already have the identity, the binary operator, and the closure property. This already checks out a lot for a binary operation. So which one are we missing? We are missing associativity, of course, and that's what we prove over here. If we combine list 1 and list 2 and combine that result with list 1, the result will be the same as combining list 1 and list 2, and then having that result combined with list 1, but in a different order. So maybe these operations look different, but the result will be the same, because associativity is something that holds up in this case. And so with identity, with a binary operator, with closure and associativity, we can here definitely say that a list in Haskell is a monoid. And in this case, we created the lists this way and this way, which is how we can create lists in Haskell. But let's look at an example in Kotlin, of course. So this is the Kotlin example for a monoid. The first property that we can find immediately is the binary operator. In Kotlin, the binary operator is this plus that we use all the time when we want to concatenate lists. But don't even think that we are actually dealing with a monoid. Sometimes, maybe not everyone, but many people use this without knowing that a list is a monoid. So that's a binary operator. So let's see now, how about closure? Closure in this case is proven with this operation over here, which of course I'm using code test assertions. So that means that when I do a should be a type of, the result is also the tree collection one, that then I can add to this one. Then I will get another list which has type array list of trees. And so the type is consistent. We get one element, another element, two operands, which combined together result in a result that has exactly the same type, an array list of tree. We have a binary operation, we have closure. Do we have an entity? Yes, we do. That's the empty list. And one thing here that is very important, an empty list in Kotlin, if we call the actual function empty list, that empty list is a literal. I will explain that in the video that I filmed before, that I will show after this. And then finally, of course, the associativity property. If we concatenate the collection A with collection B, and then concatenate the result with collection C, we should be getting the same result as combining tree collection A with the result of tree collection B and tree collection C. We've got a binary operation which is plus, we've got the identity which is empty list, we've got closure, and we've got associativity. That means that a list in Kotlin is also a monoid. So now it's time to roll out the film that I filmed before about monoids. I will come back later to give the introduction to monads. To see what monoids are and how they work, we should go back now to our Kotlin test drives project. And there we can go to this folder over here. Monads are nomads. And inside of it, if we go to the test folder, we should be able to see a test that is specific for monoids. And one of the important things about monoids is that they have three properties that we need to respect in order to call something a monoid. And for that, we can go through notes, particularly by universities. For example, we can look at the notes for the Maryland University, and there we can find this description of what a monoid should be. And it says there that a monoid M is a set M with a binary operation star that satisfies the following properties. There are three properties. One is closure, the other one is associativity, and the other one is identity. The closure only means in broad terms that if we create a result from a binary operation, the result of the operation will remain in the same domain. And that means that we get an object that should be of the same type of the elements of the operation. Then we have the associativity operation. This should be fairly familiar, and if not, the idea is that we can exchange the position of the different elements of the operation and obtain the same result. We can try to easily define what identity means, but in this case, there are three ideas behind this identity. One is that if we perform an operation with an element against the target element that we have, the order shouldn't matter and we should get the same result, but also the result of that operation should be equal to the element itself. So that's why we have here E star A star E, and just A, and all of them are equal to each other. But in Kotlin, we can also check this and see if one of the types that we want to test is actually a monoid or not. A list is in Kotlin a monoid. And to check this, I have created three tests so that we can see an example running of why a list should be a monoid. In the first example, I call the test should test monoid list to have an identity. So this is one of the properties that we have just seen in the list, and in this example we find that an empty list could be an indication that a list is a monoid. What this means is that if we try to add an empty list to a tree collection, which is this list over here, it is created with a range of numbers from 1 to 10, and those are mapped to a tree type, to instances of a tree type, that where each element contains 10 leaves. And so if we go back to our example, we see that when we add an empty list to a tree collection, the result should be the same as if we would add an empty list to the tree collection. And the result should also be a tree collection, and that is an example that I could also add here. So for example, if I pick up this part over here, and then I do it like this, and then I add, and then I say that this should be the tree collection, this example should run without any faults. And that's exactly the result that we get here now. And we can see that all of these assertions ran correctly. And this proves the identity property of the list. So we only need to test now 2 more properties. And the second property that we can test is the closure property, which is a bit more complicated, because when we are working with Kotlin, we are also working with Java types under the hood. So that means that we need to be careful with which types we are using and comparing our collections to. So the first line of code means that I am creating a pre-tree collection 1, which is a list of 2 different trees. And the trees have a list of leaves, it doesn't matter which ones. What's important here is that we create a list of trees, and then because of the different Java types between Kotlin and Java, I need to call that toList to make sure that I get the exact list type that I am using with the tree collection that I've just shown. And I do a print line there so that we can clear that up and see why I have done this. But the whole point is that I have created now a list of 2 trees that are different than the trees in the tree collection. But if I add them together with this plus, which is our binary operation, then that means that the result should only have types of trees. And this would satisfy the closure operation. So if I run this, the same thing should happen. The test should run correctly. And we see that it has run correctly. And we can also find here under the reason why I did that toList, because in the first case, when I made it pre-tree collection 1, the type is arrays $ArrayList, which is a different type than just ArrayList from Java util. But the whole point is that our binary operation is still the same. It's a plus. It has been applied to lists, and a list in this case still complies with the idea that it is a monoid, because we were able to perform an operation with 2 different elements that result in an element of the same domain. But we still have another property that we want to test, and that property is the property of associativity. And in this last example, we see that we have a test here that is called should test monoid list to have an associativity property. And here I have created 3 different collections. And these 3 different collections contain 2 different trees. And the only thing that we're going to do is to sum all 3 of them in different ways. So in this assertion right over here, we first sum the tree collection A with tree collection B. And then when we have the result of that, we add the tree collection C. And again, it is the same binary operation. And then we try to assert if that result is the same as adding B and C, and then adding that to collection A. And it should not be a surprise now if we run this test that the assertions run correctly and that there is no fault reported, because essentially what we have proven here is the property of associativity. Lists, in this case, because we can apply a binary operation, and specifically in Kotlin, in this case they can also be considered monoids because they satisfy all the three different properties that we have seen in the notes for the University of Maryland in this case, which we can find these notes in all kinds of universities. This is just a random example that I've picked up on the internet. This is an example of a monoid, and that is a list. But let's check other examples like either, like optional, and see how that works and if those also comply with the idea of a monoid. Lists are an example of monoids. But what can we say about option, for example? We have seen that before, that it works really well as a functor and it matches all the characteristics of a functor. But does it match the characteristics of a monoid? Let's have a look. When we look at this example right over here, we can see that I have tested the option against the three different properties that we have mentioned before. So let's recap. It was identity, then we had the associativity option, and then we also had the closure option. As we look now at this test, we may be led to believe that the option is a monoid. This type, maybe it's a monoid. Let's have a look more closely into the test. So right over here, I am testing that the identity property stands. Then I check here if the closure property stands. And then right over here, if the associativity property stands. And as we look at all three, it seems like everything is okay. But there is a difference. I have modified option to be able to comply with all of the properties of a monoid. However, the way I did that is simply creating an extension function for the option tree, and option tree now is extended to have a plus operation. And the plus operation in Kotlin we create by means of the operator modifier. And that means that we can use plus freely for the different operations we want to execute, and then it will work as a binary operator. So that means you will have option as an operand A, N as an operand B, and the result will be C, which will also be an option of tree. But now if I remove this and I comment it out, we'll see that the code does not compile anymore for any of the three options. Because that's kind of also the magic of a monoid, is that it is entirely dependent of one binary operator that for the most part will comply with the three different properties that a monoid should have. So what this means and what this tells us is that although an option can be a functor, it doesn't necessarily mean that it is a monoid. Does it mean that it will be a monad? Well, we'll have to wait until the rest of this video to be able to assess that. But for now, keep this in mind. An option is not a monoid because it doesn't comply with any of the properties that a monoid should have. It is a functor. And because it is a functor, we can make interesting things with it to transform it and make it a monoid-like type. If I reinstate this extension function once again, the code will compile again. And this is interesting because now, if we look at the first test, we see that the testing that the custom monoid option has an identity will work. And the reason for that is that I can create simply a tree with no leaves that I will assign to be my identity value, and that identity value can be added to another tree that does has one leaf, and by adding it to it, it will result in a tree that has the same leaf. And otherwise, it will also return the same tree with that leaf. And as a result, it will also be equal to the same tree with that leaf. If we run this test, it is now obvious with what I said that it will run without any faults. And that's exactly what we see right now. The test ran correctly in these two assertions. The first assertion with the combination of the identity value and the second assertion with our value being checked against the sum of our value with the identity value, which will be itself. And that's why this test now works. One thing though is that we consider tree in all of these cases to be the same, our tree with leaf, although technically behind it, the tree object itself is a different one. Because when we are making an addition with this operator, we are effectively creating a new tree with this copy. That's essentially what's behind the extension function that gives the appearance that the sum with our identity object doesn't change the actual tree. It does change it technically, but that's not what we see in the actual values in the code. So this tests the identity property of this custom option that we have created. In the second case, we will check for closure. And closure is very simple to test. It is quite easy to just see from our extension function that the result is actually an option tree again, and in this case is a sum. But before I continue to explain what closure means for our type option and how we are changing option to behave like a monoid, we need to pause for a moment and see what we have done so far and if we have made the right decisions in that respect. Option is inherently not a monoid, but we are making changes for it to have a monoid-like behavior. But in the process, we need to be careful about a few things. Is it possible to change it to actually be a monoid? There might be a way. And in order to do that, we have to go back to what we did. And for that, I will compare this code that I have changed already to achieve that with the old code that we had before and that I presented up until this point in these series of videos. So let's now compare it with the correct revision. And this is the correct revision. And if we go all the way to the test that was checking for our option object to have an entity, we will see one important thing. In the old code, I was creating an empty option with a tree with no leaves on it. And this is this one. And that is this one. But this object has a very important flaw in the set of characteristics of an identity. It cannot be an identity because this one is an object. And what we need for an identity is a literal. What is the difference? In this case, we have a reference and we have a value. The reference is this one over here, option tree empty. And this whole thing here is the value that is attributed to that reference. And on this side, we don't have a local object that is an entity. In this case, we are calling an empty option tree, just like over here. And we are testing for the identity. Now this works. But what is the fundamental difference here? If we go all the way down in the code and we check the old implementation, what we used to have before, we were simply summing the two different trees. And that's why we have over here this map over here, which will copy the leaves of the second operand with the first operand. That is the second tree with the first tree. It looks good, but it fails to acknowledge the fact that one of the operands may be the identity. And in that case, we don't need to perform any special operation. But this is always doing that operation, because those options that we were referring to as entities, they actually have trees that have no leaves, which is an odd concept. It should actually be something that would say to us immediately that it is an identity. Well, that identity is what I have created right over here, which is something that I have created over here, and that is a function, and that function is calling our identity, and our identity in this case is none. This none is interesting because this none is simply an object that is also an option of nothing, while being an option as well. So that means that this none is really our identity, because this none is only a literal. It's a value, we can reference it, but it's still just a value. And in that case, every time we use none, it is the same none all the time. And so the operation that we have specified, our binary operation, is a bit different now. It starts off with a when. And this when is going to check if this is none, then we will return anyways the second operand. Because even if the second operand is none, we have to return one of the nones anyways. But in this case, we return the second operand. In the second case, the second operand is the one that may be none, and in that case we return this. And otherwise we just make that operation that will sum up the leaves of our trees in our option object, which means that we return a new object. But that is understandable, and that has nothing to do with the identity. It's just the result of the binary operation that we are running. This identity was the only thing that stood in the way in that nuanced way of thinking of saying, I have an object with a monoid-like behavior, and saying, I have a monoid. Because now we do have an option that has been changed in such a way that it has an identity that is being used in this binary operation that satisfy the idea that A plus identity equals to identity plus A equals A. And so this is no longer a monoid-like object. We can say that this is a monoid, that we have changed option to be a monoid. Much in the way of a list, because before we have mentioned that a list was a monoid because it had an identity, and that identity was an empty list. But not just any empty list. Our empty list in this case is also a literal. And maybe this is one of those literals that are not well known in the Kotlin library. If we go to empty list and we check what it has this actual empty list type. It returns an empty list type. And if we check what it is, this empty list type is an object. An object of what? A list of nothing. Just as much as an option of nothing. And so we can use this very well in operations, but list has already implemented its own binary operations, which is what we use with that plus. And that plus, that binary operation, is of course something created with the operator modifier in Kotlin. So now let's go back to our example and finish off what we were saying. But now we can say that option now, after this modification, is actually a monoid. And to satisfy it being a monoid, we need to revise two more things. One is what I was already talking about in the last video, and that is the closure property. And the closure property simply just says, as we have seen with the list example, that if we sum two of these elements, the resulting element will be of the same type. So that means in an operation where A plus B equals C, A, B, and C are of the same type, which is kind of what I test here. Essentially, I'm testing that option tree color black, the first tree, should be of type sum tree when added to an option tree color orange, which should be of sum type tree, means that the result has to be a sum type tree. That means that A plus B equals C, which should be of type sum tree. And the following test checks for associativity. And associativity in this case means exactly what we saw in lists. So that means that A plus parenthesis B plus C equals A plus B parenthesis plus C. Just as we see over here. So this means that adding the option tree color pink to the sum of the option tree color black with the option tree color orange should get us the same result as adding the option tree color black to the sum of option tree color orange with option tree color pink. And this is how we just changed option to not only behave like a monoid, but to actually be a monoid. It's time to have a look at code from the source, from the originals, from where this revolution in functional programming started. And that is, of course, going back to Haskell. And from there, we can see where these ideas have come from. In this project, I have, in the meantime, added more examples, and now we have a new folder, which is the folder that has monoids in it. And there we can find 7 examples, and we are having a look at them right now. The first example is this one, monoid example. And in the monoid example, we are going to create a custom monoid. This is something that we can easily do in Haskell, and that is with the use of semigroup, which is a type that is specifically created to make our own monoids. And also, we can find the monoid declaration for character. Now, character is our custom type, and we now have to understand a few syntaxes related to Haskell to be able to continue to understand this example. In this first part, we are declaring a data class which is named character. And character has 2 different properties. These are name and age, and we need to derive them, of course, from show and generic. Then we need to define our character as a semigroup type. And this semigroup, what it does is establish different kind of paths for our code that will define our monoid. In the first line, we can see this operator, and now I have to explain what this operator is. This is also called the monoidal append operator or the mappend operator. The mappend operator in this line is defined to as return a second character when the first character is of this value. In the second line, it's the reverse. And on the third line, we create a combination of 2 different characters. We define this ourselves. Another way that this operator is also commonly referred to as is as a combinator, because it does combine 2 different operands. In this case, we have this operand, which is character 1, this operand, which is character 2, and the combination of the 2 characters, we'll see that the new name will be a concatenation of name 1 and name 2 with a space between them, and the age will be the sum of the 2 characters. But this only defines the semigroup, which is where we define the results of the different operations, of the different combinations that we expect to find when calculating this result. And just below it, we see the definition of the monoid type for character. And it shouldn't be surprising now to learn that Haskell does have a monoid type, which is where monoids come from, because the monoid type asks us to define a mempty and a mappend. Now we already know what a mappend is. This is the monoidal append operator. But mempty is our identity character. Mempty is an interesting property of monoids in Haskell because sometimes we can automatically have it defined for us, and sometimes we need to custom make it, which is what we see here for our custom character that now is also a monoid and a semigroup. We define mempty as a character with no name, or better said, an empty name string, and aged 0 years. And then we define our monoidal append operator or our mappend operator, which we say that it's this one. There are other possibilities for these operators, but for now, for these series, let's just stick to this one, which is our binary operator also, and it is composed of the lower than and the greater than symbols combined together. And then finally, we can see our example in the function main. And in main, we have a character. The first character is called the smith, and the age is 2000. Let me know in the comments where do you think these characters come from, by the way. The second character is character Lilith, and it has an age of 1000. So there will be a combined character, which will be the combination of character 1 and character 2. We also say that we have an empty character, which is simply the mempty of type character. This will result in character 0 with name empty. And then we also have the combined character 1 with empty and the combined character 2 with empty. These are just characters to test mempty, in other words, to test our identity. So in this case, we get a combined character 1 with empty that is the result of combining character 1 with empty, and then we have combined character 2 with empty, which is a combination of mempty and character 2. And of course, this one will result in character 1, and this one will result in character 2. And then we can print all of these variables to the console and see what happens. Shall we do that now? Let's do it. So if we go to Monoids in this project and then run ghc1 monoid example dot hs, then we will have our binary, and then we can run it. And then here we can see that we get character 1, which is the smith with an age of 2000 years, character 2, which is Lilith with an age of 1000, character with empty 1, which is still the smith with age 2000, and character with empty 2, which is Lilith with age 1000. But then we have the magic of monoids, which is then we get our combined character, which is a new character, which is called the smith Lilith with an age of 3000. The first is a concatenation, and the second one is the result of the sum of the two ages. Finally, at the end, we print our entity, and our entity is our mempty, and our mempty is an empty character with a name empty and age 0. So now let's have a look at one example that is very simple. This is list. We have established already that in Kotlin a list is already a monoid. But how about in Haskell? Does that repeat? Well, if you see that the example is here, you can already be assured that list is also a monoid in Haskell. But let's see the difference between a custom monoid and an already implemented monoid in the Haskell libraries. It's just this. So we don't need to make anything to turn a list into a monoid because it is already a monoid. And if we check on list 1, we see that list 1 is composed of 1, 2, and 3, and list 2 is composed of 4, 5, and 6. When we combine the two lists, we should have a concatenation of the two lists, which is also a name that this operator gets called to frequently. List 1 empty is again the same test for the identity, list 1 combined with mempty, and then list 2 empty is mempty combined with list 2, just to see if the order plays any role here. If we now run example 2, we just need to run ghc 2 hs. Now we get our binary, and then we just need to run to monoid list. And there we see that we get list 1, 1, 2, 3, that's the first print out. Then we get list 2, which is 4, 5, 6. List 1 with empty returns, of course, list 1, and list 2 with empty returns, of course, list 2. But the combined list is then 1, 2, 3, 4, 5, 6. But what is our mempty here? Let's have a look. So let's say that we do a put string, new line, and then we say identity. Which one is our identity? As I'm writing this, you probably already know what it is for a list. It shouldn't be hard. It should be an empty list, right? So let's see what happens. We get an error here, and I did this on purpose because mempty is actually a call. We need to define our identity, and to get our identity, we need to specify the type that our identity has. And in this case, the type is a list. But list, not list written as list, instead with square brackets, and then we need to define that our list is of type int. But this isn't enough, because we are defining here a type, and so we need to put this inside of parentheses. And so if we now run this, we see that the result is what we had before, except that now at the end we see our entity printed out to the console. And those were my monoid examples. We are now having a look at monads. So what are monads and what do they do? First, let's define what they are. Monads are obliged to have a type constructor. And a type constructor is as simple as saying that we need to create a container that will keep context, and that if it keeps the context, it means that it keeps a monadic context, and it wraps that monadic context around values. If we think about this through the lens of a list, then we see that a list is a container that gives a monadic context to a value, and therefore that is our type constructor. Another property that monads need to have is a unit or a monadic return. A monadic return is difficult to explain in Haskell because we first need to know what exactly is this. A return A in Haskell is not a typical return to a callback. It's not a return to a call point. It's not a return to anything really. It just means that we are returning a monadic context to A. It can mean potentially, depending on how we write the code, that we are giving back here a list of A, or an array of A, or an option of A, or an either of A. It truly just depends on how this return is declared in our code in Haskell. But a great way to analyze what it does is simply to look at what list of does in Kotlin. A list of creates a list of all the objects that we pass in as arguments. So that means that the return A in this case is creating a monadic context around A, and that results in this M over here. And this is just to say that monads need to have at least one of these functions. Another property that they need to possess a bind operator. A monadic type needs to be able to work with a bind operator. And that in Haskell is what we see over here. This is also called the monadic bind. And the monadic bind is very much what we have already in Kotlin, and there we call it flat map. If you know what flat map does in Kotlin, you should also know that that is the bind operator in Kotlin. What it does is what it's defined over here. When we have a value A with a monadic context, and then we apply that A and submit it to a function that transforms A into B and gives B a monadic context, the result is B with a monadic context, which is different than where we originally started. And this whole instruction over here is what we also see when we work with flat maps in Kotlin. Now monads need also to follow some laws. And there are three laws that the monads follow: the left identity law and the right identity law. Left and right identity laws are called that way because of the location of the return in the definition. But there's a purpose for this. In the left identity law, what we are saying is that when we wrap a monadic context in A and then apply a function to it, that will return a value that is exactly the same as if we had called the function directly. At this point, let's think a bit about what just happened here in this declaration. F, to be able to work in these circumstances, needs to be able to create a monadic context for whatever value is passed on to it. 'So that means that we are essentially, in other words, flat mapping whatever the result of this function may be. But this function, if we're talking about lists, it is going to have to return a list. So a flat map on a list where the function used creates a list results in another list. And so that's why this one here is the same as this result over here. And we can see that also in the right identity law. But we can also see over here one interesting thing, and that is that when we have A already in a monadic context, which is equivalent to having trees already, and we simply apply a return, which means applying list of directly to the receiver, then the result should be the same that we tried to flat map. It works kind of analogous to how identity works. If we think of identity, we kind of understand immediately what this is about. We are flat mapping using a function that returns the same monadic context to the same value without any changes, and so we get trees. The key difference between left and right is exactly this position. As we can see that return A is on the left-hand side of the monadic bind, and here the return is on the right-hand side of the monadic bind. That's the only reason why they're called left and right identities. And finally, we have another property that monads share with monoids, and that is the associativity law. And the associativity law says something interesting. Rather than using composition as we have seen in functors, which can be easily confused with this over here, it is using the concept of flat mapping on results. And that means that we can group here this flat map here on the function, because these functions that we are using here are returning a value wrapped in a monadic context, and so flat map here works just as much as it works here. And as we have seen before, a flat map of f in these circumstances, and because f gives it a monadic context, means that the result is something with a monadic context that we can then flat map again to get something that also have a monadic context, and so on. So that means that if we have trees and we apply flat map of f and apply a flat map of g, having f and g being separate functions, the result is exactly the same as flat mapping from trees with a function which is a combination of calling f on x, the receiver, and then flat mapping that with function g. Monads can be looked at this way. I have here a container that has two containers, and those containers have cars in it. As a result of applying a flat map on them, we get one single container with all the cars in it. If we think about it this way, then we can understand all monads. And they don't have to be lists. They can be anything. And that's what these containers here represent. For any kind of type that it's able to do this, or something similar to this, and there is a flat map operation, the odds are that that is a monad. And now we can have a look at an example of a monad in Haskell. Proving that a type is a monad in Haskell is not a trivial thing to do. But we can have a look at this example and see what happens. Just as much as in the other examples that I've shown in Haskell, we have a lot of printouts, variables defined, and functions that can test what we are going to test. So the first thing that we need to see for a list is that we have a type constructor. Is how we create a list with type int. And this example is all about a list of integers. We also have a monadic return, which is this return. For a list, we also have a bind operator, which is this one. This is the monadic bind operator that we have seen before. But it's when we start testing the 3 laws of the monad that we see this in action. And we will see then how return, the bind operator, and the type constructor play out in those tests. And the first test to look at is the right identity law. To test the right identity law, we are having a look at if by receiving a container, which is a monadic context wrapped around some value, which is represented by this m alone, and we apply there the return, as we have seen before, this will return the container itself, which is what we have over here. Then we can test the left identity law. And the left identity law says that if we receive a value and we wrapped around a monadic context to it, and then apply the monadic bind with a function that gives a monadic context to the variable, whether it creates 1, 2, 3, 5 values, the result of this operation should be the same result as calling the function directly with value a. And that's what we are testing here. So these two would return true right over here and right over here. I am testing these further in the videos that are coming up, but for now we need to get the idea that the left identity test and the right identity test will result in a true result if we run these tests. This code is all available on GitHub, and I will show at the end of the video where to find it. If the right identity law tests work and the left identity law test work, and we have a bind operator, and we have a type constructor, and we have a monadic return, then the only thing that we are missing now to test is the associativity law. And the associativity law tests something quite simple. That is simply checking if by having a variable wrapped in a monadic context and flat mapping it with this function and then flat mapping it again with this function, the result of this whole calculation should be exactly the same as using that container directly here, making X our receiver, and then creating a function for our receiver that is a combination of calling the create2element function on X and then flat mapping the result with create double element function, essentially creating an association between them that results in the same value. This should prove that list in Haskell is a monad. But how about checking this in Kotlin? The next example is about Kotlin and checking if list in Kotlin is also a monad. So this is our list in Kotlin, and the first thing that we want to check is if there is a type constructor for list. We do have a new array list if we trickle down the way we call list of in Kotlin. When we do that, it does create an array list. So if we use list in Kotlin, we are using a type constructor. So in that sense, list does comply with that rule. It also has a monadic return, and in this case, this is the list of, which is also the unit function, at least conceptually speaking. Because a list of does create new lists. So it gives a monadic context to any of the values that we put through it. And so it does work as a unit or a monadic return. Another property is the bind operator. Now the bind operator, as we have seen before and as I have mentioned is our flat map function that uses another function to give the receivers a monadic context and then return a result with it. It's important to notice that if the receivers are already wrapped in a monadic context, for example in a list of lists, that means that we don't need to wrap them in a monadic context. Flat map only works if the return result of the function is something with a monadic context. And if it is a list of lists, then a direct return will be something that already has a monadic context, because it will just be a list of elements. But these are the three different properties that list already complies with. But again, we need to check the three different laws. And so the left identity law is proven over here. And as we have seen before, in the left identity law, we are just testing if using flat map results in the same values if we call the function directly. So if we create a monadic context for our tree and we flat map that and use function f, which then is forced to give it a monadic context, that result should be exactly the same as just calling function f with tree1 as an input argument. For the right identity law, we have seen that this has more to do with how identity works. So in this case, if we have a list of trees and we flat map it using no special function, just using a return, or in this case, just using a list of the receiver value, then that result should be the same as a list of trees. And if all of this complies, and that means, of course, that the last law that the list needs to comply to is associativity. And to test that, we can see right over here that what we have done is, first we check that if we apply a flat map to trees with function f, and then apply another flat map to it with function g, then that result should be the same as applying a flat map to trees in the same way, but using a function that is created by making a first call to the receiver, to the function of x, and then applying a flat map to it with function g. And this whole thing over here proves the associativity law. But we will see again in further examples how the associativity law, the right identity law, and the left identity law play out with the other three properties of a monad to prove that list is a monad in Kotlin. So a list is a monad in Kotlin, and it is also a monad in Haskell. And we have just went through all the different properties and laws that are necessary to identify a type as being a monad. So now it's time to roll out the last sequence of videos that explain examples and go deeper into how these monads work in action. I'll see you afterwards. And finally, we can now have a look at monads. And how do we define monads and what do they mean? There are 6 rules that define what they are. And for that, one of the things that we can do is have a look at sites that talk about that. And one of them is the site of the Faculdade de Ciências da Universidade do Porto. And here we have an interesting post from Pedro Vasconcelos, that's one that's over here, where it is described what a monad is and how it works. This document is based, what it says here, from the Monads for Functional Programming document originally made by Philip Wadler in 2001. We can download the PDF over here, and this is the link to it. And here we can find what are monads for functional programming. There are examples here in Haskell that we can have a look at, but it's time now to have a look at all of these definitions. And one of the first definitions is that a monad must have a type constructor. And a type constructor is a constructor where we need to define a type. So it's just a very simple definition. And if we think of a monad like list, we can see that when we create a list, we need to have some way of defining which type a list have. So if we have a list of numbers, normally that list of numbers get automatically defined as a list of integers, but it can be a list of anything, a list of strings, or any other kind of list. And that is basically what a type constructor is. This is a common property for other different types as well, not specifically to monad, but it has to be one characteristic of the type that we are evaluating if it is a monad or not. One other thing that the document describes is that it needs to have two operations. The first operation that is described over here is the return, and the second is the bind operation. The return operation here makes a reference to how we in Haskell can define giving a monadic context to a value. This is something that in Kotlin is akin to just saying list of. When we do a list of and create a list from numbers, that is equivalent to this return in Haskell. Maybe not exactly the same, but it is essentially one operation that is very similar to the return operation in Haskell. Then it mentions the operation bind. The operation bind is akin to what we in Kotlin call the flat map. And with bind, we can flat map a monadic type. And if we look at this particular definition over here, we see that it says that a return of A is equivalent to giving a type constructor M a value A. So that means that we give a monadic context to value A. And here is the same, the bind operation that returns a monadic context. It only means that we are simply creating an operation that uses a function to transform whatever monadic value we put it through. And when we add a monadic context to whatever we create inside that function that receives as a receiver the actual value, it will return another value wrapped around a monadic context. It sounds complicated, but it really is simple to understand if we think about what flat map in Kotlin does. So in Kotlin, when we have a list of lists, each one of those lists that are part of the larger group of lists has several numbers. When we apply a flat map to it and don't do any particular operation and simply flat map whatever the receiver is, then we end up getting a result that has a monadic context. In this case, with a list of lists, we get a list of numbers in the receiver, where then the flat map operation will result in having only a list of numbers with all of these numbers that were contained in all of the different lists of the major group that is also a list. And that's where we come to this point, monads in Haskell, where there is a simple definition of everything we've just discussed here. These were already three properties of what a monad should have and what should it comply to. This is a class. In this definition, we are saying that the monad that we are using of this type M is a type constructor. And in its definition, it needs to have, again, the return operation, this one over here, which is also known as a unit, and this bind operation, which is akin to having a flat map in Kotlin. But if we go further down, we see there are three more properties that are very important, and they are actually called laws. And described in this document, there are three laws. These are the generic laws that monads must comply to be called a monad. The left identity property, the right identity property, and the associativity property. The associativity property is very similar to the associativity property that we have seen before for monoids. For monads is slightly different, but the principle behind it is very similar. For each one of these properties, let's have a look at examples in Kotlin as we talk about them. Before I explain what this means in left identity, let's first have a look at the unit test that checks for and tests the left identity of the monad list. And we can already assume that a list is a monad. If we go to this test over here, where we say that we test the left identity law of the monad, and let's bear in mind that this is the left identity, and I will explain in a bit why is this called left identity, but I can only do that when I explain the right identity as well. Then we will see the difference between the two of them. So in this case, we are creating a tree over here, and we are creating a function that will receive the tree and will set 10 leaves to it, essentially creating a new tree with 10 leaves per tree. But in this case, the resulting tree with these 10 leaves will be a modification of the tree that we have put in as an argument. Now, we have a function that is function f, and if we now use that function f in that flat map, having prior created the monadic context around tree1, and that is with list of, and that is our unit function, then we should be getting the same result as a function of a tree. F of tree1 should be exactly the same as list of tree flat map f. This tests the left identity law. Let's run it to see if it goes successfully, and we get a successful result. And so in short, this means that we had a tree, we created a list with it, we flat mapped it with function f that creates a new tree with 10 leaves based on the first one, and then we should get the same result with that as calling the function f with argument tree1. But this is the left entity. The right entity tests something a bit different, and we can see here in the test, if we just analyze the test, we see that we get a tree1, and then we create a list of that tree1. So again, we have a list of one tree, and then we flat map those trees directly using the unit function to create a monadic context around our value, and then that gets flat mapped, and that should result in the trees from the beginning. What is the difference between this right identity law and the left identity law? From this code, we can just infer that the right identity law tests for the identity. But that's not the whole story. So for that, let's go back to the documentation. But here's the thing. In the meantime, I've already changed that documentation. And now I'm using the slides that I have created based on the documentation that I have shown throughout the videos that you have seen in this playlist. And so let's have a look at the slides now. In this slide, we see the definition of monads. As we have seen before, we have seen that a list of type T, that is our type constructor. The unit is our list of, which is now represented here with this return of A, which gives it a monadic context, analogous to list of, which then returns A inside a monadic context, in this case is M. This is equivalent to do a list of A. Then we've got the bind operator. As we have seen before, this is our flat map. In this case, the bind operator is this one over here for Haskell. And what we see is that when we use the bind operator, what happens is that we use value A inside a monadic context. We put it through the bind operator, essentially flat mapping, and then we use the value A directly to change whatever we want or to create whatever we want, and then we only need to return something that has the same monadic context as the initial value that's wrapped inside that monadic context. And as a result, we get B, which is another result, another value, which is also wrapped in the monadic context. This is akin to having a list of something that gets transformed, and then finally, after flat mapping, it comes up with another value in another monadic context. And we can already see here a similarity and already a difference between monads and functors. If you remember from functors, it was kind of like doing the operation MA to MB directly. So it was a one-to-one transformation. In this case, we're not doing that. In this case, we need to have a value wrapped inside a monadic context to perform the flat map, which gives us then just values wrapped around one monadic context. And the two laws that we have seen in action are the left identity law, which is this one over here, that says that the return of A, which means the list of A, when flat mapped with function f, should be the same as calling function f directly with value A. which we have seen in our Kotlin code something like this. And for the right identity law, we have seen that if we have a value A wrapped in a monadic context, and then we flat map it and use simply a return that is the value wrapped in a monadic context but without any single transformation, we should get the same thing as an output. So we get A inside a monadic context in the same way as before, which is what we saw here when we flat map a list of it, in this case, essentially coming from a list of trees, flat mapping the result of creating a list of one tree should get us the trees. The reason why they are right and left, or in this case left and right identity laws, is because the return A here is on the left and the return here is on the right of the flat map operator, in this case the bind operator in Haskell. The last property that we look at in this case is associativity. So let's go back to our Kotlin code and see that in action. In our Kotlin code, we have one last test that says should test associativity of a monad. What we do here, we create a tree, then we create a list of trees with one tree. Then we create a function that will use a tree and transform it to another list of trees. And then we have a function G that will transform the input tree and will just give it one leaf, removing all the other leaves that it had before, essentially creating a copy of itself which contains only one leaf. But the idea here is to get to this last expression where we are testing if we flat map the trees with function f and then flat map the result with function g, we should always get the same result as if we flat map the trees and then use the value passed from that flat map with function f, which we then use to create a result that we can then flat map to g inside of the definition of the function that we are using for this flat map. Both this result and this result should return the same. And that is the way we can define associativity of a monad in this case. So if we run the test, it should run successfully. And it should run as successfully as running the right identity test, which I didn't run before, but I will run now. And so we have proven now the left identity, the right identity, the associativity. We have seen that there is a bind operator. We have seen there is a type constructor. And we have seen that there is a unit function, just as we have seen here in our slide, where we see that unit is also called a monadic return. And so this is what we saw in our example. And this is the rule that establishes it. So the rule says that when we have value A, again, wrapped in a monadic context, and we flat map it with function f, and then we flat map the result with function g, it should be the same as the same process, but when we flat map it with another function, which is using function f inside of that function to flat map the result with function g. So when we change the order, the result should not be affected. That is probably the simplest way to say it. No matter how we associate the different flat maps, it should always turn out to be the same result. Now this, of course, is for Kotlin. But we should also have a quick look at the example in Haskell, where these things originally come from. So in our Haskell test drives project, there is a folder called Monads, and inside the Monads folder there are a lot of examples, but we are only having a look at list for now. And this is list. This is the example for list. And so if we go all the way up here, we can see a few things. The first thing is that we are defining two functions. This in Haskell, as you have seen before, is a definition of a function. This is the implementation and creation of that function, the same way over here and the same way over here. Now we have two functions. One is called create two element function and the other one is create double element function. The first function simply creates an array of values based on the first value that is given as an input, and then it creates two different values for that array. One is the actual value that comes in and the other one is the addition of one to that value, and then we return an array of two values. The create double element function simply multiplies the input argument and multiplies by 2, essentially just doubling it. This is all followed by two tests, the left identity test and the right identity test. These two are also functions. For the left identity tests, we simply receive a value and then we return if it is true or not, because what we are doing inside of the test is using the return to create a list with value A, and then we flat map that, and then we see using create two element function will result in the same result as calling the create two element function with the input argument A. The right identity test function, it's the same, except that it receives as an input parameter not just a simple value but an array of one value or more, and it returns a boolean because it is testing if the value that we receive, value m, which is already wrapped in a monadic context, is the same when having applied a flat map directly to it and simply using a return on it will return the same value in that monadic context. As we have seen before, this is the right entity law of the monads. So we've got a test for the left identity law of the monads and for the right identity law of the monads. And further down we have a few other examples, but these are not mandatory properties for a monad. Maybe a subject for a next video. But for now, what's important here is that we understand what this test is doing. So if we read the main function from top to bottom, we see that we first create a test value, which is an integer of value 5. We create a test list, which has values 1, 2, and 3. And then we create a list of lists, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this is followed by several printouts. In the first printout, we see that we are simply printing out the return of test value. This should create a list of integers with one element. That's what this whole thing here does. In the second operation, we are just printing out the result of a flat map operation on the test list. We have seen here that the test list is a list composed of 1, 2, and 3. These are 3 integers. And then we apply this flat map operator, and then what we do inside of it is that we get the element of our list as an argument without a monadic context, and then we turn that into a list, therefore giving it a monadic context where we multiply every element by 2, so we double every one of them. So that means that on the output here we should be getting a list of 2, 4, and 6. After this example, there's another one, which is another flat map operation, and this one does a flat map of the list of lists. And this list of lists is what we saw here, a list of lists composed of 3 lists, where the first one has 1, 2, 3, the second one has 4, 5, and 6, and the third one has 7, 8, and 9. When we apply the flat map on this operation, we should be getting for an x value each one of these lists that then immediately returns, and therefore the result of this flat map is what we are used to seeing in Kotlin when we do a flat map, and that is that all of this list will be turned into one single list of all of these elements, and there will be no sublists on it. On this next example, then we are testing the left identity, and the left identity is simply calling the left identity as we have seen before with the test value, in this case is 5. And this will test, if we go back to the top, it will simply test that when we get here a 5, it will then do a return of it. That means this will be a list where we then apply a flat map, and then we will get a result by calling the create two element function. The create two element function will then create a list which will be of 5 and 6. And when the flat map returns, that result should be the same as calling the create two element function with value a. In this case, the value a will be 5, and therefore the result will be again the array of 5 and 6. After that, we test the right identity law for the monad, and in this case, we put through the test list. If we go back to the top and we see the right identity test, we see that we get this list over here, and then we use that list to apply a flat map to it, and we return it without making any transformation. So in that case, the result should be again the list itself. And then to complete all the tests that prove that this is a monad, we call the associativity test. I didn't mention the associativity test because I had put the bonus above the associativity test function, so we can now have a look at it. When we call this associativity test, we are putting through the test list. We receive it over here. This will be our M. That is a monadic context, and this will simply test what we have seen before when we make different calls to a flat map under different kind of associations between them. So on the left hand side of this equal operation, we apply the flat map directly to M with function create two element function. Then we apply flat map again to the result of that operation with function create double element function, which should be the same as applying the flat map with another function that we create on the fly that consists of calling the create two element function directly on X and then applying the flat map on that with the create double element function. So that means that we create a two element function and then we apply the double element function to it. Therefore, as a final result, we should just be getting a list that has been doubled and also has more elements to it, both for the first case and for the second case. We will not see the results of these transformations, but we will see that the assertions will all be true. And to see the result of these operations, of course ignoring the bonus tests, but remember that they do exist and we will be seeing them in another video, we now only have to build our example with GHC, and after it has been compiled, we only have to run it. And there, we see that all of these operations turn out to be true, and we see the result of the first operation, which is we create simply an array with 5 using return. Then we are using the flat map operation simply to double all the values inside that original array. Then we just use the flat map operation on the list of lists to finally get a result of 1, 2, 3, 4, 5, 6, 7, 8, 9, which is the merge of all of those lists into one, in other words. Finally, we see that the left identity works with number 5. We see that the right identity works with the list 1, 2, 3. We also see that the associativity works. And with all of this, we were able to prove that a list is also a monad in Haskell. If we go back to our slide, this is what we've proven both in Kotlin and in Haskell at this point. We've seen that both of them have a type constructor. List has a type constructor also in Haskell. There is a unit or a monadic return for Haskell and also for Kotlin. There's a bind operator in both cases. There's a left identity law and a right identity law for both cases, and there is an associativity law where they both comply to. So this is essentially what monads are. In the project Haskell test drives, there are a lot of other projects that you can also have a look at. I have examples here with either, examples with maybe, and other custom examples, which can help understand how monads work and how they are built. But before we conclude this presentation, it's also nice to have a look at this example, the monad custom, because this is where we can build our own monad version in Haskell. And Haskell is great in that because in Haskell the instance monad does exist. This monad type exists and we can use it to define our types. In this case, I am creating a box that of course derives from show so that we can print it. And here we define that our box is also an applicative, and we define it as being pure, and then we simply define it as being a monad by saying that the return is pure and that this is how we define the mapping operation. And the bind operation in this case simply receives a box, which is our monadic type with value x, and then we define that we use function f for the flat map operation, which then should be the same as calling the function directly with value x. Here we define a simple test function just to be able to work with our box, and this function simply says that, and this box function is simply a function that receives an x and then uses that x to double it and then create a box with it, thus creating a new monadic context. Therefore, to make our test, we create a boxed value with value 5 on it, and then we try to flat map it with the box function. This will work because the flat map uses a function that creates a monadic context to the value that is passed through. Therefore, when we print the boxed value right now, we should get a box of number 10. So if we build it and then we run it, we see predictably that we get a box with number 10. Those were my examples for monads for this video. We have reached the end of our long video about explaining what functors, monoids, and monads are. It's time now to think a bit about all of these three different paradigms and what influence they possibly may have in our code and how we work. To have these concepts present all the time seems something that doesn't happen generally these days. Many people may use a flat map and not even thinking that maybe that's a monad. We may also use concatenation operations and not even think about that those things maybe are monoids. And maybe we are just transforming data in a one-to-one basis and using map everywhere in our code base, especially if we are working with data, and not even think for a moment that all of those types are most likely functors. But why would it be important to know exactly what these things are? As we have seen in the three different cases, these follow certain specific rules. And if we have these rules present, it is my belief that we can better structure our ideas and come up with better solutions for our everyday problems, whether those problems are professionally or in our hobby projects. It doesn't matter. If it helps, then it's good to know. And if it makes the process of finding a solution better and eases that process, then it's all good that we learn these things. But maybe a question that you may have is this mandatory? It's not mandatory to learn. It's not mandatory to find better solutions. But in every single circumstance, it is always good to have a way to better structure our ideas. And that is what I tried to do with this video, to put out an idea that is, hey, why not learn about these concepts and maybe, just maybe, make better code anyways. And having said that, I still want to show something else about functors that I didn't mention in any of the videos before, and that is this. In this code, I am testing composition, and we have seen something similar in the videos when I was testing composition and see how it worked with this compose over here. But that is part of Project Arrow. If you want to test this in a different way, maybe in a more efficient way without using external libraries, we can also test it like this. Just simply calling function g on f and using the result of it as an input argument for function g. Both of these will work, and if I run this one, we can see that the test runs successfully, and if I run the second one, we will also see that the test runs successfully. And both of them are ways of testing the composition law of the functor. That's all I wanted to show for functors at this point of this video. And what I also want to say is, there may be other questions about these topics that we have discussed today in this video. It is important for me, for the channel, but also for you that have a question, to put that question down in the comments. And the reason for that is that if you put that question there, then I can answer that question. I can help, I can clarify, and I can also provide some kind of advice in solving problems where I may not have the answer for. But I can also always help. And that is the point of this channel, and that is the point of these videos that I'm making. So it is important to leave your comment, or if you prefer, to participate in the community tab of the channel. I am posting there constantly now a lot of quizzes. They are all different subjects. Some of them touch the topics that I've mentioned in this video. Some of them talk about functors. Some of them talk about monoids. And others talk about monads. And those are just different quizzes. And sometimes there are posts. But in any case, there's always a way that you have to participate in the channel. So please do so if you want to participate. Don't hesitate to participate in the channel. You are always welcome to ask questions and share your ideas and thoughts in this channel. These are the resources that I have used to create this video. This is where you can find the source code and the documentation that supports this video. And finally, this is a list of links in social media about me. I have an home page, my LinkedIn profile, my YouTube, Blue Sky, Mastodon, GitHub, HackerNoon, DevTO, and Medium. Finally, all I want to say is thank you so much for watching this video. Make sure to subscribe if you are finding this channel useful for you. Give a like to this video, a big thumbs up, of course. And I'll see you on the next video. Have a good one.
As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.